Hello community! Today we go beyond LoRA and merging LLMs. Today we're going to talk about LLMs for LLMs, and we're going to talk in specific here about composing augmented language models. So this is what you know. We have here our classical pathed LoRA. We have a multi-LoRA adapter scheme. We have our mixture of expert system, you know those videos. And we have here the ability to merge models. And I'll show you here the Merge Kit Python notebook from Maxime Leban. I use this. I think it's a very excellent model. So if you want to merge different models, this is the notebook for you. You see the Colab notebook link here at the bottom. And of course, you know, this merging has been going on for some times, you know, July 2022 here, this model soup. And then here, October 23, this ties merging by here, University of Northern Carolina, IBM, and MIT. You see this is here one of the different merging options that you have in this particular Jupyter notebook. We are operating here on specific task vectors, but of course we have other methodologies, for example, negating here a task vector, or even before here merging models with here some special averaging. So today I think we're rather standardized here how to merge models. Beautiful. Now we have here our self-attention transformer network. You know, currently there's a little bit of a hype about here this state space model here, remember the S6 model. And of course we have now constructed here our mixture of expert, our multiple member MOE here, January 8, 2024, and it tells us, hey, look, with this mixture of expert of member, we can now achieve the same accuracy with only here about a 2.2 less training steps for the classical member. So you see, we are just following the same pattern. But how can we invent something better? So, you know, if we have LLMs, those LLMs can talk to each other, they can talk to databases, they have real-time data integration. And if you see here in this video, I show you here with a modular RAG for 2024, we have close to 100 different RAG systems. And if you're interested in one of the most advanced modular RAG system, I have here a video about self-RAG explained. We have a self-reflective AI with multi-AI agent. But you know what? We want to go beyond this RAG simple, because RAG is just that the LLMs communicate with each other, but we want to have an integration of the pattern recognition intelligence of each LLM. We want to go deeper. We want to combine their intelligence and not their output. So therefore, beyond RAG. What are the critical parts here if you go with a parameter efficient fine-tuning with a low rank adaptation? You know, it is challenging if we use this for a complete new knowledge domain. Let's say your model has been pre-trained, for example, here on English, and then you have here a LoRA, pathed LoRA adapter on, I don't know, Mandarin, a complete different language. You know, it's almost impossible to do here a parameter efficient fine-tuning since we have a complete new domain. Now we are looking for something to enable here a model to be adapted to complete new knowledge domains using here an augmented model. So not like RAG here, an augmented prompt structure, but we want to augment a complete LLM. And if we do the merging of LLMs, so we take one LLM and a second LLM and we cut off, I don't know, the bottom and the top half, then we merge those LLMs with their layer structure together. This only works in a very limited amount of times when the original models or LLMs are very well aligned from their architecture, from the architectural point of the layer configuration. If you try to merge two layers that are completely different architecture-wise, it will fail. So here, we want to be more generic and a new methodology that we can apply any set of models, compose and combine any set of complex LLM almost independent of their layer structure. And we want to use this with a minimal specific training data set. So you can see that I'm talking about composition of capabilities of, let's restrict ourselves at least to 2 individual models. And this is what we are focusing now. And you know, January 4, 2024, Google Research and Google DeepMind, some specialists, some geniuses here, shows us how to do this LLM, augmented LLM. We expand now the capabilities, not just the output communication, but the inherent intelligence that has been learned in the weight structure, and we compose here multiple LLMs. And we do this here, of course, and you guessed it, with a cross-attention mechanism. Since the mathematics in this is not really trivial, so for my younger viewers, just want to give you a very simple introduction to the topic. Imagine we have a small little LLM, it's a fine-tuned LLM, A, with some frozen weights, and then we have a big, very capable, for example, logic reasoning model, fine-tuned an LLM B. We call this the augmenting model, and it has a something special learned, a specific numerical sequence, for example. And then we have our anchor model B, and this has here been trained on real complex arithmetic algorithms. So this is here really able to have here some logic reasoning, where more or less here we might only have specific data sets. And what we want now is not just the output that these two models can talk to each other or be chained together. No, we want more. We want much more. We want to touch the intelligence of those models and combine the intelligence. And this, of course, in the weight tensor structure of the model and the particular dimensionality and the way they are built. So you guessed it, what we're going to do. Since we assume that both models have frozen weights, we cannot learn new weight structure. Those weights are there. We need them for the calculation, but we do not modify the weight structure, neither in A nor in B. And this is what makes it so efficient. We don't touch what it knows. We want to have this knowledge for us, but we have new learnable parameter. Remember in LoRA, where we injected new trainable tensor structures into our adapters. Now this is the same, more or less. So we have now a projection layer. And this is here a function of a projection here. And what the simplest way we have here simply a matrix, a tensor. And of course, this will be a learnable parameter. So if we have here let's say a small dimensional model and here a high dimensional model. Now it's easy. We just have now to project here this dimensionality to a dimensionality that is identical to our anchor model, to our big model. So this just maps here a specific layer representation from our model A to the dimensionality of a layer representation of the model B. So to be compatible with each other, we have to have here a projection mechanism. You know this, an easy operation. Now you might say, hey, if this model has 24 layers and this model, let's say also 24 layers, you ought to say, hey, for example, we go and we take every fourth layer, so 4, 8, 12. So now you know how you combine layers. If you think that you're just going for the higher valued layers at the top end of the spectrum, you can find your own linear combination of those layers. Beautiful. So now we have compatible layer, and now you know that in the abstract we use the cross-attention mechanism. You know exactly what we do. We apply now a cross-attention. So just to be specific, H, as I use here, denotes a specific layer representation of a given input of a specific model. Let's say A here, model A or model B. Add here the specific layer, for example here I. So this is what H stands for, and now we have a dimensional representation that fits exactly. We can do our mathematical operation, and this is why we do this. So here we have it. This here, as you can see within the parentheses, we have here our projection of here this specific layer representation of our model A and the ith layer here. So this is exactly what we're looking here. And we combine it now here, or we calculate here the cross attention with here the layer representation of our model B, and we have here a specific layer the layer J. Now, as you can see, we have now two different sets of trainable parameters because here our weights are frozen, and here our weights are frozen. So we have to inject new parameters that learn new things, given here the frozen weight that we will use only to calculate, but not to modify. Beautiful. So this is it. So we have here projection tensors to learn and a set of cross-attention layers to learn, and you see here our W0. And then what we do, the next step is rather easy. We take here exactly here this cross-attention output, and we add it here as a residual connection to the layer representation of our model B, of our anchor model. And this now in total is here the input to the next layer, to the J+1th layer of our composed model. And so we go through the layers. So you see, it is rather easy. The idea is simple. We project here to have a comparable dimensionality of our complexity of the architecture of our layers. And then we just use here the cross-attention layers with learnable weights. And we have then a training data set. And the model learns here this composed model from model A and model B. Now, you noticed I was a little bit, I just said here, yeah, this or the hat, you remember? But this expression is a little bit more complicated. So let's look at this hat configuration now in detail, how we can calculate here a multi-large language model cross-attention in detail. Now, we go through the same mechanism again for Ben, for my younger viewers here. Look here, we have 0.1 to 9. So again, two models, A and B, and we have here different layers. Then we have here a selection of specific layers for our cross-attention. Then we have a projection for the dimensionality alignment of both layers. You see here the projection function that I showed you before, where here our W projection is a new trainable projection matrix because our weights are frozen of both models. So we have to construct some new tensor architecture. And then, of course, here, and this is the most important part 4, in this cross-attention mechanism, remember we have here also, think about self-attention, query, key, and value matrices. So for each attention head, if we go for a multi-head attention, let's look at a single attention head with a cross-attention module. You have the queries from the model B. Remember, this is here our anchor model, and this is here the layer representation of a specific layer in our anchor model. And you have for the cross reference here, the key and the values from the model A, from our augmenting model. And this is nothing else as here the projection layers. So now you feel familiar. We have our key and value pairs from model A, and we have the queries for model B, and we do a cross attention between the now dimensionality equal coherent layer that we have chosen, specific layer here we have chosen, and we do here the cross attention calculation. Cross attention calculations, you know the scale dot product query and key scaling factor is this. And then you know the output and the attention weights are computed here as this with the softmax function. You know all of this. Then we apply here the attention weight. The output of the cross attention layer is as I showed you already here. And this output is the input to the next layer. Then you have optional some normalization, nonlinearity you have to take, and then you pass it on to the next layer. So cross attention allows here the model B to dynamically integrate information from the model A, our smaller augmenting model, effectively allowing here B to ask A about certain features or patterns in the data. And this is especially useful when we possess here specific knowledge or capability that the model B is lacking. So we can enhance the representation of performance here of both systems. Now, If you want to have even a little bit more detailed dive here, look, it is absolutely the same topic. We calculate here the cross-attention mechanism in CALM in our composed augmented language model. But here you have a little bit more of the dimensionality that we are operating here. So for each layer L in the model A and B, you know this, then we have here the projection. Beautiful. We have here the projection matrix. Now, please note that this is H model A layer I dash. So whenever you see a dash here on top, this is here simply the projection tensor applied to it. And then you have the query key and value matrix construction. So for each attention head, remember multi-head, learning the weights yes are introduced. So look now, the query, you remember the query are coming from the model B, and we are going here for the layer J. And this is simply here what we already looked at here from the projection. And then please note key and value are from the model A. We have the layer I. And now please note here we have here the HAI dash. And you know, dash are here with the projection. So this is the difference here coming from B and having here the projection of the key and value. Then we have the scale dot product attention calculation. This gives us here the probability distribution. The output for each head is then the weighted sum of the value matrices using this attention weight. So here you have now this formula that you already know and love. And then for the multi-head attention aggregation, you know how we do here. Multi-head, we concatenate this exactly with all the different heads, and we have a W0. Then you have, some layer normalization, backpropagation, learning. So what you have, what are now the trainable tensor structure that we inject into this composed model? Now, you know we have the projection here from the model A. Then we have our query tensor, our key tensor, our value tensor, and our W0. And W0 is here from the multi-head structure. You see, this formula is absolutely identical. Let me go back here to this here. We just wrote it different, the combination of the different heads. And here we have our W0. You see, easy explained. Great. With this explanation, now we can jump to the original publication by Google. And look here, this is just one paragraph about how to calculate here the cross-attention layers of a composed augmented LLM structure. And this is exactly the formulas we went through. This is exactly the notation that I just showed you. And you see the result for the cross-attention output is added as a residual connection to the layer representation of B. And the resulting output vector in turn is the input to the next succeeding layer here. And this is exactly what I just showed you and how we went through this calculation together. So you see a projection and a cross attention. This is all that we need. Beautiful. Now we achieved now something great because now we just have injected those different trainable weight tensor structures. And now we just need a data set that combines here for the model A, the capabilities with the capabilities of the model B. We just let it train a little bit. And then our additionally injected CALM tensor, if you want, here in our cross-attention layers, in our projection layers, are learned. And now the composed model of both LLM have now a knowledge and is able to perform tasks that neither of model A nor B could do alone. Notice that this is not at all limited to just one small augmenting model and one small anchor LLM. You can have multiple augmenting models, HA1, HA2. So for example, you can have an augmenting model, I don't know, about a specific topic in theoretical physics, and HA2, a specific topic in theoretical chemistry, and you combine it with, I don't know, kind of a GPT-4 structure. So you can have now, instead of fine-tuning here one huge model on a data set that the others have been trained for, we have now the opportunity to use the inherent intelligence of the model that are already there, already available, and we can combine it in a much faster, more cost-efficient way. And I will show you the performance is identical if we would use all the training data and do the classical fine-tuning on our anchor model. Yeah, and for you here, the composition to augment language model here, if you want to look here a little bit more in this projection functionality in our projection layer, our first layer that we have in COM, I've written here this for you, but it's already explained. Now, what are the application? The author used it here for some key value arithmetic or for some low resource language inclusivity. For example, you have a translation from a model B and a model A that has been trained on different languages, and you can compose this now if the syntax of the languages are somehow comparable in a much easier and faster way than to train here your anchor model here on a new language. Great. Experiment results, everything looks beautiful. So what we have achieved, we have here a big anchor model with a lot of logical reasoning and small expert models. And now, instead of models talking to each other via chained whatever, we have now a new mechanism to directly touch here on this pattern detecting intelligence of our tensor weight structure in the model A and the model B and combine this to get new capabilities. So we have here model A, model B, and somehow we define here on this interwoven new structure, we train it here on some advanced knowledge application. And I think this is a fascinating new step that goes beyond LoRA adapters, that goes beyond here all mixture of expert models, that goes beyond here merging models, because we can now opt here to explore, complete, and integrate new knowledge domains. Here, for example, from the original Google publication here, so the question was, hey, what does this Python code do? And you put in a code snippet of Python, and then you have here this augmenting LLM that has been pre-trained on GitHub examples. And you have, for example, let's say GPT-4 with its beautiful formulation and augmentation capability. And if you do not have now in this code snippet, of course, here in the comments that it explains what the code is doing, but that if it's just naked code without any commentary, the system would now be able to understand what the code is doing, and the system B would understand what this particular code sequence and code application is able to perform. And maybe here that is a classical word game of something is just one idea. Maybe if this is scientific code, this code you just cannot apply in physics, but maybe in chemistry or maybe in medicine. So you see, combining not the output, but the knowledge, the inherent knowledge representation in the different layers. And yes, it depends if you go here for the first layers, or you have just a linear sequence of layers, or you focus here on the last layers, or the before the last layers, to have really here the combined intelligence, what has been learned before. This is now an interesting research topic in its own. Maybe I will do a specific video on this, but you see, the way forward is now here to do this combined knowledge representation with frozen weights. So you take this model with its capability, you take this model with its capability, you do not have to retrain, refine-tune, do anything. We just inject new layers, and these new layers learn something that has not been possible to solve before. New capabilities. And here from Google, the original thing, when PaLM is augmented with some code-specific model, here, GitHub, for example, we see a relative improvement of 40% over the base model. So the performance of B increases for 40% for code generation, which is on par with a fully fine-tuned counterparts. So if we would now train B on GitHub and have no A at all, then it would have the same performance compared to our composition of LLMs, where it is much faster. We use already the intelligence of the model A here, and it is cheaper, faster, and gives us the same performance than to fine-tune B. Amazing. It's really a kind of a revolution to combine the knowledge of multiple LLMs together. And this is what I tried to depict here in this beautiful generated synthetic image. You have two LLMs. One LLM is on a specific topic, and then you have a beautiful, let's say a big, complex LLM for reasoning. And you can combine it here with injecting additional layers, additional architecture of a tensor weight, learnable tensor weights, and you just have more or less the projection layer and then the cross-attention layer. And you achieved to extract here the combined knowledge of both models. And here, that what you get out of this combined model is more than the sum of the parts of the model. We generated a new capability for our LLMs, and this is what I call a genius idea and kind of revolutionary to combine multiple LLMs, not over their output, not to chain it together, but really to touch here their heart, their primary intelligence, and combine those intelligence, architecture, tensor structures to achieve something brand new. I hope you enjoyed this video in the way I did, and it would be great to see you in my next one.